We can determine the convergence or divergence of a sequence if given the nth term by taking its limit as n goes to infinity. In our first example, we have the nth term of 7 over n plus 3. As n gets really large, 7 over n plus 3 will approach 0, fixed numerator, growing denominator. So that converges, that sequence. Alternating signs, be very careful. This term out here, if we let n get really large, will approach 1. But because our signs alternate, we never do settle down at a specific value. So because of the alternating signs, divergent. If that wasn't there and this is all we had, we would have a convergent sequence because of the finite limit value. Be very careful with alternating signs. Our third example, our nth term is natural log of n cubed over 6n. When you apply a limit as n goes to infinity, natural log of a really large value cubed is going to be really large. 6 times a really large value is also really large. So this is an indeterminate form of infinity over infinity. Using L'Hopital's rule, we take the derivative of the numerator. That's 3n squared over n cubed. Then we take the derivative of the denominator, which is just 6. Reducing this fraction, 3 over 6 is 1/2. N squared over n cubed leaves an n in the denominator, so that becomes limit as n goes to infinity of 1 over 2n, which goes to 0 as n gets really large, convergent. The example at the bottom, as we let n get really large, 1 over n is going to approach 0. 3 to the 0 power is 1, also a convergent sequence. Use the squeeze theorem, and we're going to use it on both of these examples to determine convergence or divergence. Now, back in trig, you learned about amplitude. The sine of an angle would never have a value that exceeded +1, nor would it be smaller than -1. So what I'm going to do is I'm going to take the limit as n goes to infinity of our original nth term. That's in black ink in the middle. Because I know that the numerator can't be smaller than -1, I can squeeze it on the low end using a -1 as the numerator. Sine can't be larger than +1, so I can squeeze into the middle from the upper end. So this -1 and +1 are the extreme values of sine n. No matter how large n gets, I know that that numerator will never go smaller than -1 or greater than +1. And again, that's back to amplitude, the lead coefficient. Now, as n gets really large, both of these limits on the end go to 0, which squeezes in this limit having to go to 0 as well. So we have a convergent sequence. Same idea in the second example. We have an nth term, cosine of 4n. The 4n just means it oscillates 4 times faster than normal, but a lead coefficient of 1 also tells us that the range is -1 inclusive to +1 inclusive. And that's why on both of these examples I have the or equal to line, because your trig functions can be equal to -1 and +1 in these examples. But by replacing an oscillating numerator with fixed values, you can squeeze in from the ends. Both of these limits will approach 0 because you have fixed numerators with growing denominators. Well, if both the ends go to 0, that forces the limit in the middle to go to 0 as well. Both of these nth terms are represent convergent sequences, and that's the long story short of it. See if you can find specific numerical values to trap your nth term.